Now, in the second part, we will be doing something else. We will be actually talking about the theory and the practice of tan delta testing. So this was just a short introduction. Well, it was 30-minute introduction, but I hope I managed to explain to you the idea behind tan delta. Now, we know why we measure tan delta, and here you can see PF. It is an abbreviation for power factor. I will explain later exactly what does it mean, but let me say that we will also talk about some other names for tan delta. You will see that another name for tan delta is dissipation factor, while the concept of power factor is being used in some other countries, for example, USA, etc., etc. So let us start now looking at the voltage and current vectors in an insulation. In an ideal insulator, in an ideal capacitor, we have an ideal insulator. We have 90 degrees shift between current and voltage. So this is the voltage which we apply, and this is the current which is caused by that voltage. By the way, tan delta test is an offline test. I didn't mention it before, but you cannot do a tan delta test while the asset is being used. What you can do, if you want to continuously measure tan delta, you can install sensors, and then you will have an online monitoring of tan delta, which is different. I mean, again, you're measuring the same thing, but today we're talking about offline testing. So that means my testing equipment will apply a voltage, and then it will measure current. And this is one of the testing equipment which we use. Later you will see some other. This would be an STS 5000, and this would be the TD 5000, which will apply up to 12 kilovolts. But we know that we are not dealing with a perfect or ideal insulation or a capacitor. We are dealing with a real insulation, and we learned just a few minutes ago that a real insulation or a real capacitor has a resistive current which is passing through this resistor here, which means that the total current is the vectorial sum of IC and IR. So what we can say is that the total current is the sum of charging component and the loss component. And we have to say that the charging component is much, much bigger than the resistive component, but the resistive component, as we said before, is not zero. And this is how you would draw this in Cartesian system. You would have an IC here and IR here. Now, I would like to draw one thing for you. Of course, in this case, we made IR very big, just for the sake of, let's say, correct definition. But what I would say here is important to say is that, as we mentioned before, IR is very, very small. So it would be more like maybe this big. So if you would sum up this vector here and this vector here, you wouldn't get something like this. You would more or less get something like this, something which is very close to the y-axis. So this would be your total current. And just to give you a heads up, you see this small angle here? This small angle would be your delta. And you will see that just a small angle delta might wreak havoc on your primary equipment. So let us finally define what is a tan delta. Tan delta is the ratio of in-phase or resistive current to a 90-degree or capacitive current. And we can see tan delta is IR over IC. If we play a little bit with the formula here, we can also see that tan delta is a reciprocal value of omega RC. This is a constant number. If we are doing a test in a European country, this would be 314. And if we do that test where the nominal frequency is 60, it's slightly higher. But anyway, you could see that the resistance and the capacitance with which we model the insulation are needed to calculate tan delta. So tan delta is the tangents of this angle here. And this angle is usually very, very small. For power transformers, 1 degree, you are already in trouble. I will show you later what is the limit, but usually this is a very small angle. Another name for tan delta is dissipation factor. And dissipation factor has been used in some other countries. So let's say in some countries they say I'm measuring C and DF instead of I'm measuring tan delta. And then there are some countries like USA which use the term power factor. Now actually tan delta and power factor are very, very similar. They're very similar because you see, tan delta is resistive current over capacitive current, while power factor is resistive current over total current. And since we said that this angle is very small, let's say this would be your total current, whether I'm dividing this length with this length here, IC, or this length with this length here, the yellow line, it wouldn't make much difference. So one could say also that power factor is cosinus phi, while phi would be this angle here, or IR divided with I total. And of course, there are formulas which can convert one into the other, so this one and this one. And you see, we will say very soon what are the expected values, but let me give you a preview and say that these numbers are very small. Actually, they're very close to, let's say, 0.001 or 0.1. So if you factor that in while looking at this particular formula, you will understand that power factor and tan delta are the same. Actually, for the values of delta, of this angle here, up to 10 degrees, power factor and tan delta can be considered the same value. And one could say that tan delta, and if tan delta and power factor are different, then the insulation is already compromised due to the fact that the angle is too high. So if you have already more than 10 degrees, if your delta is more than 10 degrees, we already have too much resistive current, which will in turn then destroy our insulation. But how does the insulation actually get compromised? Well, what happens is that the insulation gets older. It gets old. All of us, we get old, and all of us, including the transformers, breathe. We said before that the transformer breathes. So for those of you who know, just bear with me. And for those of you who don't know, imagine a situation of a 250 MVA transformer, which is a big transmission transformer, which is supplying a city of 100,000 people. During the day, the temperature outside is 30 degrees Celsius or 25 degrees Celsius, and the transformer is being used to power air conditions and people's lives. People are awake during the day. The transformer is maybe used at 70 or 80% of nominal power, and inside the transformer, the oil increases its volume. And as the oil increases its volume, it's simply bigger. But then the night comes, the temperature drops, people go to sleep, and the transformer is not used anymore 80%, but maybe 20 or 30% of its nominal power. And since the temperature reduces, the oil reduces its volume. Then again, the morning comes, the oil increases the volume, the night comes, it decreases the volume. So I hope you follow me and you understand that this is a definition of breathing. The same thing when you breathe. If you want to breathe in, you will expand your lungs, your chest, in order to suck the air inside. And then you will contract it to push it outside. The same is done with the transformer, and that's why transformer has a breather. The breather is that pipe through which the transformer breathes. At the beginning of that pipe, you have some silicon, which is put there for a reason, which is to remove all the water molecules from the air. And it does a good job. You know that you need to change that breather when it changes color, sometimes from blue to white, sometimes there are some other colors. But the point is that even though you have the breather, it is not perfect. Like ideal transformer, it doesn't exist. There will always be some water molecules which enter the transformer. And these water molecules contribute to the conductivity of the insulator, of the oil. And also these water molecules usually inhibit, they stay in the cellulose. I would say 90 to 99% of all the water which is in your transformer is actually in the cellulose, in the paper and the press board. It is not in the oil. Another reason how our insulation is gets compromised is, let's say, partial discharge. So partial discharge inside the transformer is a process where we have small sparks, let's say between the high voltage and the low voltage, or maybe two windings, etc., etc. And in this process, the gases are developed. And unfortunately, the gases also increase the conductivity of our insulating system, which is a problem. Also, we have oxidation process, which creates a sludge, which also reduces the insulating properties and increases the conductivity. Acidity changes, and all this contribute to the deterioration of insulation. And let me give you some numbers now. How do we know that the result is good? How do we know that we measured a good value for tan delta? Well, I would say that this, what you see right here, which we will discuss right now, is also standard, but it is not the only standard. So this is an IEEE standard, and for a new transformer, in general, the tan delta or dissipation factor should be less than 0.5. Then, if the number is between 0.5 and 1 for a service stage transformer, then we talk about also good insulation, acceptable insulation, and only if tan delta is bigger than 1%, only in that case we have the right to suspect that there are some problems happening inside. So what I'm saying here is that maybe you have noticed that all of a sudden I've started using percentages. Well, I'm using percentages simply because when you do a tan delta, when you measure a tan delta, you see you have two values which are both amps. So you get a number which has no dimension, but that number is usually 0.01 or 0.05 or 0.005. So instead of saying 000, you just multiply that number with 100, and then you slap the percentage sign onto it, and then you express yourself in percentage. So long story short, tan delta should be less than 1%. So this is what we talk about when we talk about transformers. But in preparation for this webinar, I have went through some articles, and there was an interesting article. This is an article which was made by Mr. Rajani Menon and his collaborators. Here, you actually have four, let's say, categories. We talk about extra high voltage transformers, and then, let's say, medium voltage transformers, and then again, we have some high voltage transformers, and then we have some standard distribution transformers. So why have we done this? Why have they done this? Because it is not always the same whether you have a weak insulation at 400 kilovolts or a weak insulation at 10 kilovolts. Of course, if you have a weak insulation at 400 kilovolts, it's a bigger risk than having a weak insulation at 10 kilovolts. So we could say that there are different values for a transformer tan delta values for these transformers. So for example, what you can see here is that the values for extra high voltage go from 0.2 to 0.9. And I want to turn your attention to one more thing. You see that here we don't talk about only one number. We have three values which we will be talking about, because we have an insulation between high voltage and low voltage. We have insulation between high voltage and tank, and low voltage and tank. And you will see later what I mean by this. So for now, what we can see is that for extra high voltage, the insulation between high and low voltage side, the insulation should be very good, between 0.2 and 0.5, which is much less than 1%. High voltage versus tank is between 0.7 and 0.9. If it's smaller, even better. And low voltage tank is between 0.4 and 0.8. And also we have some capacitances here. Now, a capacitance is really difficult to assess. It's not difficult to assess, it's difficult to say what would be the nominal values because it depends heavily on the construction, on the design of the transformer, on some of the materials which are being used. But these are some, I would say, guidelines when we talk about capacitance. And capacitance for a power transformer are expressed in nanofarad, and capacitance for bushings are mostly expressed in hundreds of picofarad. Now, when we talk about, let's say, medium voltage transformer, then we see that high voltage, low voltage, tan delta is between 0.3 and 0.6, but high voltage tank and low voltage tank can go up to 1%. Then, I would say a standard high voltage transformer, 132 to 11, would be between 0.3 and 0.6 for high voltage and low voltage, and between high voltage and tank and low voltage and tank, you could have a little bit more margin. And then last but not least would be a distribution transformer. In that case, since we don't have a very high voltage levels here, the tan delta can also be higher, even up to 2%. But what you need to observe is that high voltage, low voltage is always the one which needs to be the smallest. The tan delta for these insulation needs to be the strongest because this is, let's say, the important one. Now, I hope this part is clear. You are encouraged to ask questions. So Sertal asked, is there some standard about tan delta level for high voltage transformers? So I hope this is answered by this slide here. And another thing I want to answer is, I haven't mentioned before that all these values are at 20 degrees Celsius. Tan delta depends on temperature. It's temperature dependent. And we can see here what is the temperature, what is the formula, how to recalculate tan delta onto 20 degrees Celsius. You see, if tan delta at 20 degrees Celsius is 1, it is the same like having tan delta of 3 at 70 degrees Celsius. So what you need to find out is what is the temperature of the oil on your transformer. You simply read it from the gauge which is installed on the transformer, and you factor that in after you measure the tan delta. Because if it's 50 degrees outside and you guys got, let's say, 1.8, it doesn't mean that your high voltage transformer has a problem. It simply means that you need to compensate for that temperature using this formula here. So I hope that that is clear. Now, moving on, how to interpret results. Also, I'm having some questions about negative values of tan delta in a transformer, so let me address that right away. There are a few reasons why you could get a negative value for the tan delta. One of them is you are not performing the test properly. This is very often the reason. It's a sign that you didn't connect something correctly. Another reason could also be that the grounding of your substation is not done properly, because then you are also not able to properly assess, to properly measure tan delta. Grounding is essential because we measure also the current going through the ground. And one thing which Mr. Simone Meneghin mentioned, because we did have that same question in the morning session, is you need to understand what is the value of tan delta, of this negative tan delta? Are we talking about minus 7% or minus 0.01%? Because if you have minus 7 or 3 or 1.5%, probably you have issues with the execution of measurement. You are not measuring correctly. But if you have minus 0.01, in that case, you are probably dealing with a very good insulation, and the accuracy of the measurement is maybe not that great. So while measuring the current and while calculating tan delta, there might have been some errors which happened while calculating tan delta. So the tan delta, negative tan delta, it means that this vector here, it means that this total vector is not 90 but more than 90 degrees. And this can happen sometimes. It is not a physical reality, it is actually a problem with the measurement. In your case, what I would do if I had a situation like that, I would repeat the measurement, and before that I would check thoroughly if all the connectors are connected properly and if we are doing the test correctly. Later I will show you some tips and tricks how you can make sure that you are doing a good measurement. So let me also read the next question. How to follow tan delta according to trend recording, because one of the slides stated that the evaluation is not only about comparing to a specific value. So that's a good question, and thank you for that. So one could say that if you measure tan delta on a yearly basis, that absolute maximum of delta, of change which can happen, is 0.1%. Again, it's not written in stone. The new, I would say, standard is being written, and this will be included. But if you have a new transformer which has tan delta of 0.3, and after 5 years you measure that transformer and the tan delta is 0.9, which is still below 1, that's a sign for an alarm. So let's say that the rule of thumb would be 0.1% per year or less. And we have one more question. Please discuss how ISA tan delta measure technique and results compare with double and Omicron technique. So the results are comparable. Actually, they are the same. I had an experience. I measured in few laboratories with our device TDX and with double device M4100, and we got the same results. Sometimes they would be the same up to a third or fourth decimal. Sometimes the second decimal would be different, but effectively the differences are very, very small, or there are no differences whatsoever. So it's completely normal to use an ISA test set, for example, after you have used a double or an Omicron test set. So I hope that answers your question. Now, moving on, and we'll return to the rest of the questions a little bit later. How do we evaluate results? So first, as we said, we compare to the previous values. This is the best way how to assess your tan delta value or your power factor value, because your transformer, when it came from the factory, was probably tested for tan delta in the factory. So you do have that information somewhere. If you can dig out that information and bring it to the test site, you will see what was the tan delta when the transformer was produced and what is the tan delta today, which is something which can definitely tell you if you have an issue or not. Also, as we mentioned before, the change should not exceed 0.1% per year or less. The next way how to evaluate results is comparison to allowed values. So if you use the table which we have shown before, like this one, you compare it and the number needs to be smaller than 1 as a general rule, or if you want to be more exact, you can take a look at this table and then compare it to that. The third way would be comparison of the phases. If you are measuring tan delta on bushings, because you will see later that we don't just measure tan delta on the body of the transformer, we also measure it on the bushings of the transformer. If you measure on 3 phases, A, B, and C, you expect to get the same numbers, especially if the bushings are the same, installed at the same time and from the same producer. If a certain bushing has a higher tan delta, then what you will probably do is frequency sweep, but we will talk about that in our next session. And then, of course, if you cannot do any of these steps, sometimes you will have the same type of transformer. Let's say you will have a substation and 2 or 3 transformers from the same producer, same type, installed same age, and then you will measure one and then the other, and then you can compare between them the values. So this is also one way how to check if your results are good. Now, let us discuss what is the nominal value at which you should measure tan delta? What is the actual value of voltage which should be applied when measuring tan delta? First of all, it is not necessary, and in many cases not possible, to generate more than 12 kilovolts. Why is this so? It's so because at 12 kilovolts, all the polarization processes inside of your insulation are done. Even if you would generate 200 kilovolts instead of 12 kilovolts, you wouldn't get a different result. So first of all, 12 is, or very often people use 10 kilovolts, but 12 is, let's say, the prescribed value. And of course, you need to keep in mind what is the voltage level of your transformer. If you have 10 to 0.4 and you're generating on the low voltage side, you cannot generate more than the nominal voltage. So please be aware of that. Also, what is the testing frequency? The testing frequency should be as close as possible to nominal, so 60 Hertz or 50 Hertz. Now, there are some differences when it comes to measurement, the voltage and frequency, and that mostly concerns rotary machines, so mostly generators. Generators sometimes can be tested with up to 15 kilovolts, so 1.5 if necessary, and in that case, you might change the frequency a little bit more. In the case of transformers, you shouldn't change the frequency more than, let's say, 2 Hertz. So this is about frequency and about voltage. So here we have some of our test sets. So let me look at some questions which just came in. Negative PF is a reality in bushings with internal tracking. PF will be negative, yes. Also, tan delta is 1 over omega I RC as per equation. In this case, which is the ideal frequency for measuring the same? So I hope we just answered that. So the frequency should always be the nominal frequency. Is there a shield between a high voltage and low voltage winding? It will result in a negative value. I have to say I'm not sure if this is so, but if you could send me some ideas, some, let's say, your own experiences to my email, I would be very happy. And we will look into that. The applied voltage must always be sinusoidal. Yes, the applied voltage is always a sine wave. Can tan delta depend on measurement frequency? Yes, it does depend on measurement frequency, but not so much. Let me just say that we will talk next time about frequency sweep. This is when we do tan delta at different frequency levels. It depends on the frequency, but not very much. If it starts to depend very much on the frequency, then we have a problem with the insulation. And why is it considered tan delta value more than 1% for a distribution transformer? That means resistive current is more to produce heat dissipation. Well, as I said, these numbers are not written in stone for a transformer, a distribution transformer which has a lower voltage, let's say lower than 60 kilovolt or even lower than 11 kilovolt. You can go up to 2%. And yes, it is more resistive current, but the point is that we don't have a very big voltage. And since we don't have a very big voltage, the insulation doesn't have to withstand such, let's say, high pressures or, let's say, high differences of potential. So for higher voltages or extra high voltage, you should have lower values of tan delta or a better insulation. It's like if you have two pipes through which the water flows, and let's say that they're the same pipes, and both of them have a small leak, not a leak, a small hole, very small hole. If you have pressure of 1 bar in pipe number 1 and a pressure of 100 bar in another pipe, then the small hole in the second pipe would be more detrimental. I mean, it would be more of a risk to the system than if you would have that same hole in the pipe which would have only 1 or 2 bar. So I hope that answers your question. Please explain why it should be sinusoidal. Well, honestly, it's how the standard prescribes it, and I can just explain it in this way, because sinusoidal voltage is what is used. So the best way how to test an asset is if you use your nominal voltage and nominal current, which then replicate the whole situation, how the asset is being used. For the temperature correction factor, is it dependent on the oil condition, how old it is? No, the temperature correction factors are always the same. Temperature correction factor K is in the presentation referred to which standard? It's an IEEE standard. I will tell you later what was the exact number. Doesn't absorption current affect the results? I'm not sure I understand that. Please, can you just send me, if you can explain a little bit what you mean by that, absorption current. What is the maximum testing voltage of low voltage transformer? So on the primary side, you would generate 10 kilovolt, and on the secondary, you would generate 0.4 kilovolt. And you will see that now. Is there any chance of deferring the capacitance and tan delta measured with high and low and high? They're absolutely the same. So whether you measure it from the high voltage side or the low voltage side, the number should be the same. Is ESA building a library of test values for various transformer models and bushing models to offer as a test guide? Well, we didn't do that because in the last 7 years, actually, we were mostly being guided by the 1% value. And for a bigger transformer, that value, you see, for the bigger transformer, what usually happens is that people who are using those transformers, the asset managers, have the initial values, and we do compare with the initial values. That's what helps us understand what is actually expected from us. But I'm not saying that it will not happen in the future. So let's continue if we want to do all the steps. So on which assets can we measure tan delta? Tan delta we can measure on a power transformer, on a body and the bushing of a power transformer, instrument transformer and the protection transformer, so CTs and VTs, on a generator doing a tip-up test, and on a motor doing a tip-down test. So tip-up test is what we call a voltage sweep. Next time we will look into that, but the voltage sweep is when you do a tan delta test or a power factor test on different voltage levels. So let's say 20, 40, 60, 80, and 100% of nominal value. And then you go 80, 60, 40, 20, and you compare those results to see if they are the same. And you do the same thing with a motor. On a cable, also, on a cable you can test a power factor or a tan delta, and generally on a cable you will have much lower values. So again, to discern the values which we're talking about, these are the values for a transformer. If we were to talk about cables, then these numbers would be much smaller. And if we were to talk about generators, then these numbers would be much bigger. So for a generator, between 3 and 5%, that's a good value of a tan delta for a transformer. Now, we can also measure them on surge arresters, and as I said, we can measure them on any primary equipment which has an insulation. Now, I have another question here. There are some brands that run tan delta tests with frequency sweep. Is there a standard that validates this method? As much as I know, I didn't find any real standard, but I will dig a little bit deeper, and next time when we will be talking about the sweeps on Monday, I hope I will have an answer for you. So right now, let us see what is the correct procedure when performing a tan delta on a power transformer. Now, the first thing you need to do is when you're doing a tan delta test is to remove that power transformer from the network. You simply open the circuit breaker, you open the disconnectors so that you are the one who is generating voltage and current. The next step is usually prescribed by all the utilities. Sometimes people forget to execute that step, and if that step is not executed, therein lies the risk of damaging the testing equipment. So the thing is that you should take your grounding rod and you should touch all phases of primary, secondary, and if you have tertiary side with the grounding rod, thus de-energizing fully the transformer. So transformer needs to be fully de-energized, because if it's not, what might happen is that some remaining current or voltage can close itself through the measurement of tan delta device. And this is something which can then damage the testing equipment. The third step is short circuit. This is very important. We should short circuit fully the primary side phases ABC, secondary side separately ABC, and if you have also the tertiary side. You should do that. You will see why. And when you do that, you should also correctly ground your testing equipment. Correctly ground, it means that you ground the testing equipment in the same grounding point where your transformer is grounded. So that means that you shouldn't have two different points of grounding, otherwise the current can close in a different loop and you might get bad results. If you are now testing, the next step would be if you have STS and TD, so this would be STS and TD. Before you turn them on, you would connect them and these two boxes, and then you would turn them on, don't connect them while they are on. And if you have a TDX, since it's a one-box solution, you don't have to do any connections. So this is showing you actually how the short circuit is done on the primary side, how the short circuit is done on the secondary side, and for this example we are taking a transformer which has primary and secondary side. And as you do this, what you actually create, you create a situation where you have, as we spoke before, three capacitors. You have capacitance between the high voltage and the low voltage. You have the capacitance between the high voltage and ground and low voltage and ground. And standardized, let's say, names are CHL, high voltage, low voltage, CH, and CL. You can see that that's how this table was made. This is CHL, this is CH, and this is CL. Why is this so? Well, this is a good thing because when you do a tan delta measurement, you don't just get one number. You get minimum 3 numbers. And it's good because maybe all of them are okay, but maybe CHL is good and CH is good, but CL is bad, which means the insulation between the low voltage and the ground is not good. So you have some indication what needs to be fixed. When you do some other DC test, you just get one number, and that one number cannot tell you where the problem lies. Here you get minimum 3 numbers, and effectively you will get 9 numbers because, or even maybe 11, because you will also be testing each bushing for itself. So after you have short-circuited, you need to connect the cables. So our first step in this case will be simply to generate first on the high voltage side and measure from the low voltage side. And just to remind you, this is the equivalent scheme of a 2-winding transformer because we have short-circuited all phases. We didn't short-circuit primary together with secondary, we short-circuited separately primary and separately secondary. And also the neutral is also taken into consideration when we did the short circuit. And you can do this with a thin wire because the current flowing will be milliamps. So you don't need to use thick wires. Of course you can, but it's not necessary. With this setup, as you can see, generation on the high voltage winding and measurement on the low voltage winding, you can measure CHL, which is this one, and you can measure CH. Using this setup, you cannot measure CL. To measure CL, we'll do something else. Now, as you have connected and grounded properly your system, you need to punch in the nominal values. It's a good idea to say, well, it's necessary to say whether you have a 3-phase or single-phase transformer and whether you have a 2-3 winding transformer or auto transformer with tertiary. That's something that depends on what type of transformer do you test. But what you can see is that it's also a good idea to write what are the nominal values of your tan delta and capacitance, because then you can get an automatic assessment whether your result is good or bad, so pass or fail. And then what you guys do, you need to go into the application, and this is now the good part. In our application, when you click this drop menu, you should say, this is the answer to the question, where have I connected the high voltage generation coming from my test set? I can connect it to a high voltage winding or to a low voltage winding. Or if I have a transformer which has also a tertiary, it can also be connected to the tertiary. So right now, I have connected to the high voltage winding, and then I answer the question, what do I want to measure? CHL, which is this, or I can measure CH, or I can also measure CH plus CHL in one shot. So these are three things which I can measure with my voltage, with this setup. And then, if you're not sure how to connect, of course, you just press the question mark button and you will get this nice scheme. And also, what I wanted to say is that as you have chosen this and this, automatically the system chose what method will be used. Will it be a UST or a GST method? This is a topic for our next discussion. UST means ungrounded specimen test and GST means a grounded specimen test. So just as a preview, I'll tell you that if you want to measure CHL, you will use a UST because this specimen, this part of insulation, is not grounded on any side, while this specimen is grounded, and also this specimen is grounded on one side. So you can see that when I choose a CHL, a UST-A method is chosen. You choose the voltage, which is the maximum voltage which you can choose for your transformer, or 12 kilovolts, or 10 is also often used, frequency, and then you also choose a single test. This would be voltage sweep and this would be a frequency sweep. Here you would see your nominal values, and here you can also do a temperature compensation. Now, after doing that, you would position correctly the cursor, add test, and you would make sure that nobody is close to the power transformer. Dear friends, safety is of the utmost importance when doing this test because 10 kilovolts or 12 kilovolts or even 1 kilovolt is more than enough to damage, let's say, or to hurt a human being. So be mindful when executing this test. As you press start, you would observe the lower left corner and you would see when the test is executed. First, you would have the stage of load evaluation, then calibration, and then measurement. And actually, we're doing two measurements, and I will explain next time why. And when the test is done, you would go back to this screen, and you would just drop this menu again, and you would choose CH. By choosing CH, you would again make sure that nobody is close, press start, and you would check the results. Then you would press the emergency button. The emergency button is a very nice mushroom type red button, which is this one here. We also have it here. And this button is important because, you see, of course, nobody is going to intentionally press start when somebody is on the transformer, but nobody knows if something like that will happen accidentally. So because we are very, let's say, we care about your safety, we want you to use the emergency button. Now, as you have pressed the emergency button, you will make a switch. Now, the high voltage generation will go to the low voltage side of the power transformer, and the measurement will be coming from your high voltage side. You would configure, so I'm sorry, this would be your connection. Now, the measurement would be going here. This is called input A and this is input B, for example. That's why we had here UST-A. A means that the measurement was coming to input A. And now in this setup, you would be generating voltage here, maximum allowed voltage, or 10 or 12, and you would be measuring from here. And in this setup, you can measure CL, but you can also measure CHL. So this is one of the ways how you can verify if you're doing a good measurement. You can measure CHL from the high voltage side, then you can repeat that measurement from the low voltage side, and you can see if the number is the same. Up to a third or a fourth decimal, it should be the same. Another way how you can make sure that you are testing correctly is you can measure CL, then you can measure CHL, and then only with one shot you can measure the sum of CL plus CHL. And what you can do, what that gives you is the fact that if you sum up this capacitance and you get the same number like when you measure the sum, it means that you are performing the test correctly. So this is one of the ways to make sure you're doing everything correctly. It's not that this is necessary, but I'm giving you some tips and tricks. I'm giving you some tips and tricks in order simply to be sure that you are doing the test correctly in case there are some issues. In the past, there were some, the tan delta measurement was pretty difficult because we were not measuring, let's say that we needed to measure very small values like today, but analog circuitry was more prone to the noise. Today, we're not facing such issues, but regardless, it is something which should be taken into consideration. And now, after connecting the generation to the low voltage side, we choose what we want to measure. So as you can see, you can measure CL or CHL. So CL would be insulation between the low voltage winding and the ground. Again, CHL would be the insulation, the state of the insulation between high voltage and the ground. And CL plus CHL is here just to check if the measurement was okay. Automatically, the device would choose the appropriate method and the test would be ready to start. So again, the process is you press start, you look at the bottom left corner, and you check the result. You press the emergency button before you approach the PT, and then you start the next set of measurement, and before you do that, you remove the short circuit. You remove the short circuit because the next step is measuring the bushings. Now, bushings are actually more prone to insulation issues. And very often, sometimes actually you just measure the bushings for tan delta. Maybe you don't even measure the body for tan delta, but you measure the body for tan delta every 2 to 5 years, and bushings maybe every year. If you want to measure the bushing, in that case, there is a test plug here, and this test plug needs to be unscrewed, and then you would connect first measurement and later generation here. And then there are two values you measure on each bushing, C1 and C2. Also, on this nameplate, you would see C1 and C2 written. And as my colleague Simone mentioned in the morning, these numbers are the numbers of the tan delta of the bushing which was measured in the factory. These numbers can sometimes differ because in the factory it was not mounted on this particular transformer. So that's why these numbers can be slightly different. And if you do not have this test plug, a tap, then you can use something which we call the hot collar. It looks like a collar, it looks like a belt, like a strap. The first thing you need to do is to clean very well your bushing, and after cleaning the bushing, you should tighten it very nicely. The gray side should go on the inside, the green part on the outside, and then you would use this as your connector to measure or to generate voltage or to measure current. So this would be the scheme. You would, in order to measure C1, you would generate here and measure here, and in order to measure C2, you would generate here and measure here. So you would just shift this like before. So long story short, you measure all three bushings, and when you measure C2, please be careful so that you do not generate more than 1 kilovolt. In some cases, you can even go up to 2 kilovolts, but you don't need such a high number, and you are risking to damage insulation or to damage the transformer if you generate a voltage which is more than 1 to 2 kilovolts while generating on C2. So you would be measuring C1 and C2. You would be doing that for all the phases, and then you would be repeating that if you have that chance on the secondary side of the transformer. And then you would move on to the next power transformer. When you would finish, you would get these results. CH, capacitance between the high voltage winding and the ground, and the tan delta of that insulation. CL, so capacitance low voltage winding and the ground, and CHL, capacitance between the high voltage and low voltage winding. So this is what you would get. This is the body. And then you would get C1 and C2 for phase A on the high voltage side, C1 and C2 for phase B, and the one for phase C. And if you have also if you measure the low voltage side, you would get the same set of information. And long story short, the easiest way to interpret results is that all of them should be less than 1%, all tan delta. Capacitance, there is no standard for the capacitance. The only thing is that you should have the previous values, and if that value changes more than 7%, this is again a value I heard a few years ago, but I haven't found that in any standard, but it was more of an empirical value. If the capacitance changes more than 7%, that's a sign for the alarm. If you have some tan delta which are more than 1%, you would do a sweep to get a better view of what's happening. And we are almost done. So what I would like to mention here is, and allow me to read this, let us keep in mind that when we measure tan delta values of a complex insulation, so oil, pressboard, paper, we will know the state of the whole insulation, not just one segment. So we will not just know the state of the oil, or just the state of the paper, or just the state of the pressboard, which is a big advantage in respect to, for example, dielectric breakdown test of the oil, which that test also has its place, but you can have a perfect oil, but since most of the water molecules are in the cellulose, in the paper and pressboard, doesn't help you if you have a fully functioning oil and the damaged insulation in the cellulose. So, so what I'm trying to say here is that tan delta gives you a bigger picture, not just picture of one segment. So, because if we just test the oil, as I said, we will know the state of the oil, but we will know if it's conductive or not and how conductive is it. But if we get good results for the oil and the paper is full of water, then we're missing the big picture. And as we mentioned before, most of water stays, even up to 95 or even 99%, stays in the hygroscopic, stays in the paper and the pressboard. So we have now one example and actually 4 more slides and then we're done. This is an example of one test which we did in Russia. So it was in a city of Kazan. It was not a small transformer, it was about, if I'm not mistaken, 45 MVA transformer. This is the report, but what I wanted to show you is after you've done your measurement, for example, we measured CH, we measured CHL, and we measured CHT. So this was a transformer with primary, secondary, and tertiary winding. You could see that here we have the values for the CHL. For the CH. So this is the insulation between the high voltage winding and the ground. And you can see here that we wanted to generate 10 kilovolts and 50 hertz. The device generated 9,994.4, so this is quite accurate. The total current, which was going out, capacitive plus resistive, was about 12.85 milliamps. With our device, you can generate up to 300 milliamps. And the capacitance between the high voltage and the ground was 4.0976 nanofarad. The tan delta is the number we're looking for, and we have here 0.2283, which is more than a good result since it's less than 1%. And you can see that the power factor is the same as tan delta. And that's what we mentioned before. Up to 10 degrees, they're almost the same. And even up to 5 degrees, they're the same up to, I think, even the third decimal. So moving on, we also have this RP. So we will see that on the next slide. RP is 342.7 mega ohms. So actually, when we executed this measurement, we measured the capacitance of 4.097 nanofarad, and we measured the resistance of 342 mega ohms. So we have these two values, and if you take these two numbers and use the formula for tan delta, which is equal to 1 divided with omega RC, you would get 0.22, let me check, 0.2283 of tan delta. Also, one thing which I like to mention is that here you have the angle phi. So just to remind you, the angle phi is not the angle delta. Angle phi is this angle here. So it's this angle here. This angle should normally be 90. In this case, it is not 90, but it's 89.8692, so it's only 0.13 degrees, 0.13 degrees less than ideal. And this gives us the tan delta of 0.2283%. So let me just tell you that if your delta would be 0.52 degrees, or let me put it like this, if your phi would be smaller than 89.42, you would have a tan delta bigger than 1. This just goes to prove how small that angle is allowed to be. Or if we talk about Hans Brinker and the story about the dike, how small the leak can be to destroy the whole dike. And just to close the whole story, to explain what is the QF or quality factor, QF is nothing but a reciprocal value of a tan delta in absolute terms, so not multiplied by 100, and this number needs to be bigger than 100. If it's smaller, then the tan delta is bigger than 1%. And here we also have RS. RS can also be calculated as tan delta divided with 2 omega c, which actually tells us that if you have an equivalent scheme, which is not the connection of capacitance and resistance in parallel, but capacitance and resistance in series, this is what would be the resistance connected in series.